Yeah, so I want to talk about the mesoscale structure of the Inter-Tropical Convergence Zone. And I think from what I saw, what you listened to so far today, this is going to be a less theoretical talk. And don't be surprised that I mostly talk about the Atlantic ITZ. So this is not because I think the Atlantic ITZ is the most important ITZ in the world, but just because my recent field work has mostly been in the Atlantic ITZ. And so, yeah, I know you've talked about this a lot today already, so I'm going to be really brief on this, but just to sort of set the scene also for what I want to talk about, just a very, very brief reminder of what the Inter-Tropical Convergence Zone is. So we all know it's the rising branch of the Hadley cell, and the Hadley cell, importantly, is like a thermally direct circulation. So transports heat from where the ocean surface is warm to where the ocean surface is cold. And it has key aspects that we care about. It's marked by really high precipitation rates. So that's sort of the tropical rain belts, of course. It's marked by high cloudiness, which just also means that it's very important for the Earth's radiation budget. And I think you've had an entire lecture on this, but just to kind of summarize in sort of two dot points, the ITZ is of course also important for the poleward energy transport. And the critical points here are the vertical motion profile is sort of important for how the energy gets exported and together with the moistatic energy profile. And so what my talk was mostly going to focus on is really that this is a picture that only arises in the mean. And so what do I mean by this? So the properties I've just described are really properties that emerge when you look over like a long time scale or a large spatial scale. So if you do zonal averages or you take monthly averages or so. And on shorter time scales, what is really key is that you have this interaction between clouds and the large scale circulation. And maybe to just make this a little bit more tangible, what I mean by this is, okay, so now we're going to look at the Atlantic ITZ. So you see parts of West Africa, you see parts of South America, and then in between, this is the mean precipitation climatology for May. Just downloaded that, and you can see perfectly well sort of this tropical rain belt that we associate with the ITZ. But then if you look at what did the precipitation look like yesterday, and so I just randomly went on NASA Worldview and downloaded this image. You see the clouds, but then you also see the precipitation sort of superimposed on this. Then you immediately see that only a small fraction of the area is sort of covered by clouds. Precipitation occurs. You can go sort of back. Precipitation sort of occurs where you have the tropical rain belts, but of course not everywhere. So it's just that these intense regions of high precipitation that then in the end up making sort of the mean tropical rain belt. And so this is really key. That's the clouds. You cannot understand the tropical circulation without the clouds. And what I really always find interesting to think about is just the role the clouds play in sort of mediating the circulation. So if you think of so in your head, you have the schematic of what the ITZ looks like or what the Hadley cell looks like. And there's just this big rising branch in the center. And that's also something that emerges in the mean. So what I show here on the left-hand side is what's the mean vertical velocity if you average at like 5 kilometers height for 2 months, a limited area model simulation. And so unfortunately, vertical velocities in the atmosphere are really hard to measure, so I couldn't use observations for this. But so this is just from a simulation. And you see in red is where the air goes up, and in blue is where the air goes down, and that fits really well the schematic, right? There's a broad region of ascending motion, and then there's an even larger region of subsiding motion. But then if you look at just a randomly chosen instant in time, and that's what's shown on the right-hand side, you'll again see that this breaks up into these really tiny, strong vertical updrafts, and there's hardly any vertical velocity you see sort of in the rest of it. And what's here also really important to note is that there is 2 orders of magnitude difference in the color bar. So on the left-hand side, the color bar goes up to 5 centimeters per second. On the right-hand side, it goes up to 5 meters per second. And so what happens is all the rising motion happens within clouds. And the clouds really only cover this tiny, tiny fraction of the deep tropics. And so even within this region that we usually just draw with these two sort of arrows pointing upwards, most of the air is actually subsiding at any given time. So on average, you have this picture that emerges on the left as well. You have a band of rising motion, but at a given instant in time, that's not what it looks like. And how does that actually work? And so I give you sort of a cartoonish explanation for this. So what happens, so how do the clouds actually drive the circulation, or I shouldn't say drive, but mediate the circulation? And so what happens is that the buoyant air that rises within the cloud, so the air is just lighter, and then to some degree it's very simple, right? You have conservation of mass, and what goes up somehow has to come down. So on first order, this is very simple. But then it actually gets a bit tricky if you think exactly of what happens. And it turns out that what happens in the deep tropics is that buoyancy anomalies, so buoyancy anomalies, that's the thing you need to make the air actually go up in the first place. They excite gravity waves, and these gravity waves quickly remove sort of the anomaly and spread it over large scales. And if you're like me, then you find it's a bit hard to conceptualize in your head what that exactly means. And I always like to think of it as a raindrop that falls into a puddle. And I should say I did not come up with this analogy, so it's actually it's an analogy that I find very helpful, and I have it from my PhD supervisor, but I don't think he came up with it either. And so what do I mean? A raindrop that falls into a puddle is the same as a cloud driving a circulation. On first glance, that seems very different and very sort of hard to kind of, how would the one help you understand the other one? But so the idea is that basically the atmosphere works sort of upside down from this drop that falls into the puddle. And so what's the analogy? So the idea is that a raindrop, so sort of a dense fluid, falls into the puddle. And that's sort of the same thing as a cloud that injects a lighter fluid upwards into the free troposphere. And then what happens is that excites waves, because on the one hand, the water is much denser than the air, so there's a restoring force if you locally add water to your puddle. And in the other case, the atmosphere is stably stratified. And you can see that this is, of course, like a simplification, right? Like in the atmosphere, we have many, many layers, but in this example, we just have a single layer. But so then you can see, so what happens to this water droplet that now basically locally increases the amount of water you have at one point. And so what happens is it gets redistributed. So I should actually, this is actually what I want. It gets redistributed over the entire puddle. And the way it is redistributed is through waves. So we have a local anomaly, and then the waves propagate away and actually transport mass and propagate it away from the cloud/drop. And then eventually sort of the gravity waves dissipate, and the average effect of your drop is now that your puddle is a tiny, tiny bit higher, and that corresponds to, in the atmosphere, that you have on average sort of impose something like a large-scale subsidence. And so I'm not sure if you need this, but just if you want to sort of visualize what happens if you drop into a puddle, you can go online, and there's sort of visualizations for sort of solving this equation, and you can just see that initially you have some very well-defined sort of waves, but then they spread out and become harder and harder to see. And so what happens in the tropics all the time is that it's basically constantly raining into your puddle. And so if you look at the vertical velocity field at like a given instance in time, it looks really complicated. But sort of the average over sort of superimposed effect of all of this is that you induce constant subsidence. So you have really strong vertical updraft motion within the clouds, and then large-scale subsiding motion that results as a constant effect of all these sort of different clouds. So that's kind of how the clouds sort of make the air move. in a simple way of thinking about it. But clouds are also really critical for the vertical energy transport. And so we said before that the Hadley cell is a thermally direct circulation. And so air rises over warm regions and sinks over cold regions. And it wasn't actually until the 60s that we understood how this transport from the surface into the upper free troposphere sort of happens. So you have to, you have a warm sea surface temperature. So at one point it's warm and in the other point it's cold, but you have to sort of transport the air from the one to the other. And how does that work? Well, first you have to kind of get the warm air from the surface to the upper free troposphere. And as we just learned, or as I'm sure you probably already knew, there's no large-scale ascent that sort of transports warm air like you have in a, I don't know, if you're boiling water, then you really have a large-scale mass that transports, mass transport that transport also the heat, but that doesn't happen. So the rising motion happens within the clouds. And what was shown is that the thing that actually in the end really heats up the upper troposphere is again the clouds, and it's the condensation of water vapor that happens within the clouds. And so again, it's really the clouds that really matter here. And so what I want to point out is that you can really not understand the Inter-Tropical Convergence Zone and also not the Hadley cell without understanding the scale interaction between the small and the large scales. And so if you think of like the key aspects of the ITZ, that there's high cloudiness, there's high precipitation, what that just translates to is that you have a high occurrence frequency of clouds, and the ascending branch of the Hadley cell is really the combined effect of ascending motion that happens within clouds. And similarly, the poleward energy transport, we said before, that depends on a vertical motion profile, and the vertical motion profile is basically set by the vertical motion profile within the clouds. And so sort of in a schematic way to think of this, we have the clouds and we have the large scales. And if you want to understand what happens on the large scales, we have to understand how the large scales impact the clouds, but then also how the clouds sort of impact the large scales. And that's challenging. That has been challenging for a long time for climate models, because climate models typically resolve processes on the order of like 50 to 100 kilometers. So what does that mean? A deep convective cloud in the tropics is, can be larger, but sort of a ballpark, it's on the order of 1 kilometer. And so what that means is that in your typical grid cell, you can't actually resolve the cloud. So you have to somehow, so what you basically have to do is you have to guess what the clouds look like in your grid cell, and then you have to guess again what that makes, what impact that has. So kind of I took the most classic convective parameterization schematic that exists overall. It's like from the Arakawa and Schubert paper who developed one of these parameterization schemes. And you can see sort of there's this grid cell. That's kind of what your climate model resolves. And then you guess this cloud population inside this grid cell. And then then you guess again and see how that impacts properties like the vertical velocity, for example. So you have now within this grid cell, you have all these clouds, they have a certain vertical velocity. What does the mean vertical velocity look like in this grid cell? So far, so good. The problem is that convective parameterization schemes are tricky to develop. And one of the reasons they are tricky to develop, and we'll talk about another later, is that they are very difficult to constrain observationally. But at the same time, they're so critical because, as we said, you can't understand the global circulation without representing the effect of clouds, that this question, which seems very technical, led to the largest atmospheric field program of all times. So that was the GATE campaign that happened in 1974. And the campaign's goal was sort of in very, very general term was to explore the mechanism by which the solar heat stored in the tropical ocean, drives the global circulation of the atmosphere, and how do we incorporate this mechanism into numerical models? And so really this last part is this, well, now how do we deal with this? How do we deal with this problem? And just to kind of point out how big this campaign was, I think they had just under 40 ships, and they had, I think, 13 research aircraft. One satellite was basically launched for GATE, so it was really a tremendous campaign, which kind of shows you how much people wanted to know what is the answer to this question. And so how did they try to constrain this problem? That's also interesting to look at, because one thing they did is they basically just distributed all their ships in the tropical Atlantic. You can kind of see that on this map here. But then if you look closely, then you see that there's something that's called the East Atlantic Array, which is sort of in the eastern part of the Atlantic. And if you sort of zoom in, what that means is they actually stacked sort of hexagons of ships into each other. And so why would you do that? And the reason you want to do that is that this allows you to measure also other things, but it also allows you to measure vertical velocity. And if you find the schematic a little bit funky, it's a bit funky because my JetGPT skills are not so great, but I hope it still kind of helps to illustrate what's going on. So why is measuring vertical velocity so problematic? The reason is basically that on larger scales, vertical wind speeds are on the order of centimeters per second. So we saw that before, but on horizontal wind speeds are on the order of, say, 10 meters per second. So there are orders of magnitude between these two wind speeds. And that basically means when you build any kind of device for measuring this, as soon as you have a little bit of contamination of sort of the horizontal component of your wind field, that's in the end the only thing you can actually measure. And so it's very easy to measure horizontal winds. It's extremely hard to measure vertical winds. And so the way they did it during GATE, and to be honest, this is pretty much the same thing we do today. Usually we don't have enough ships, so we take an aircraft that flies in a circle, but the idea remains the same. So what they do is they simultaneously launch radiosondes. So at each ship you get a vertical profile of horizontal winds, but also of thermodynamic properties, right? Like humidity, temperature, pressure, and so on. And then you obtain the set of horizontal wind profiles, and then you use the divergence theorem to calculate the horizontally averaged divergence profile. And then, so you know at what level how much air goes in and how much air goes out. I mean, obviously, approximately, right? Like ideally, you would have a ship at every point. You'd have like an infinite number of ships around this area, but okay, so we kind of make estimates and we kind of decide on what's the minimum number of ships we need. And then you know how much air goes in and how much air goes out into your column at what height. And because you know that the vertical velocity at the surface is 0, you can integrate this upward to obtain a vertical velocity profile. And so basically for every radiosonde launch that happens sort of in a coordinated manner, you get one mean vertical motion profile from within this column. And you also get the thermodynamic profiles. And so then if you know how many clouds sort of were in your area A, and what the properties of these clouds were, you can kind of try to see, okay, if I have a cloud, then it has this effect on the large scale properties, or the grid cell properties, I should say. The problem is that the results of GATE show that it's not that easy. And I think they formulated that in a bit more careful manner. And so they say the results of GATE show that to simulate the effects of tropical convection in large-scale numerical models of the atmosphere, a variety of phenomena must be accounted for, including not only convective scale updrafts and downdrafts. So this is the thing we were talking about so far. You need to account for the clouds to understand this. But you also have to account for annual clouds with mesoscale updrafts and downdrafts. downdraft-induced boundary layer transformations and mesoscale convergence patterns. So basically what they're saying is, it would have been nice if this problem would just look like sort of this upper sketch, where you have the small scales impact the large scales and vice versa. But what they actually find is that there's the mesoscale that gets in the way. What does that actually mean? So what that means is that I've sketched like a couple of different ways clouds can sort of organize themselves on the mesoscale. So the left-hand part is sort of the unorganized popcorn convection, and then we have different kinds of ways in which clouds can organize, and I will talk about some of them in detail in a second. But the problem is it matters. So even if you always have the same number of clouds, and even if these clouds maybe are not so different from each other, or the clouds are different from each other, but if the say the number of clouds is the same, the way they're organized can have an impact. And so that's tricky, because if your convective parameterization scheme can't resolve the clouds in the first place, it can also not represent sort of these mesoscale organization processes. And so you actually add like another layer of complexity to your problem. And so just to make this kind of more tangible, what are these mesoscale processes and what are their impacts? And so it's really two separate questions, right? It's like the question, what does mesoscale organization do? And what creates the mesoscale organization? And I'll talk a bit about both in the next slides. And so one thing that mesoscale organization does is that it changes precipitation, humidity, and radiation. And that's already pretty much, right? Like if you think of what you care about with the rain belts, you care about where it rains and how much it rains. You kind of care about that it's a humid region because that impacts the radiation. And yeah, you care about the cloud properties because again, they impact the radiation. And so one particularly strong effect or a particularly sort of efficient way clouds have in impacting this is that they can organize themselves. And again, I think you've had a lecture on this, so I'll only kind of talk about this briefly. But this idea is that instead of the popcorn convection, so randomly distributed convection, you actually have clouds that sort of clump together. And that has been shown to have a strong impact on the thermodynamic profile of the environment, for example. And so I'm going to make it a bit more concrete. So you have these, so what does self-aggregation actually, where does it basically come from? And I think it's important to remember that self-aggregation is something that happens in extremely idealized simulations. So basically what you do is you want to understand the properties of clouds. And so one thing you can do is you can remove the complexity of your simulation a lot, because then it makes it just easier to analyze, right? Or at least you might think so. And so what you do is you set up a simulation that has a fixed sea surface temperature. It has homogeneous boundary and initial conditions, which basically just means that there's no preferred location for convection to occur. So convection is just similarly likely to occur in any part of the domain. And you force it, so convection has to occur, because otherwise the atmosphere is unstable to convection, and so convection builds forms. And what that means initially is just that you get what you were actually hoping for. You get this domain, and like randomly distributed within this domain is basically where the clouds form. And you can see that here on the left-hand side, so it's sort of a horizontal cross-section of this simulation, and the colors just give you how often did you have, or do you have a cloud at a certain location. And it's pretty randomly distributed, right? If at all, it's maybe irregular, but it's maybe another question. But then this phenomenon of self-aggregation happens, and after 50 days, all the clouds are sort of clumped together in this single cluster, as you can see on the right-hand side. And suddenly there's basically a lot of the domain is free of convection, and everything happens within this one cell. And I should say because the simulation has periodic boundary conditions, I just pulled the cluster to be in the center. So the center isn't a special place at all. It's just the center got sort of defined by the fact that the cluster was there. And at the same time as the clouds organize, so does the water vapor field. So there's a strong correlation between precipitation and column water vapor, and that's exactly what you see if you look at sort of the corresponding humidity field. So this is another simulation, but again, the same idea. You have the similar kind of setup. Initially, you have randomly distributed clouds. The column water vapor field is reasonably homogeneous, but then you let the simulation run for long enough, and suddenly all the clouds are organized into this tiny fraction of the domain. And so you might wonder, like, why would we care so much about this? You have these really idealized simulations. It's a bit unclear of how much they have to do with reality, because they are so idealized. So convection in the real world never has as much time to just do what it wants, basically. But the key thing is that as the clouds become more organized, they really change sort of everything we care about with regards to sort of the environment and tropical convection. And so one thing is they just change the mean water vapor content of the atmosphere. And so you can see, of course, that they change sort of the pattern of the water vapor content, but they also really change the mean water vapor content. And so while you have this tiny region that's now extremely moist, it really outweighs that the rest of the domain becomes super dry. And that's important, of course, because if you now look at the outgoing long wave radiation, then you have a much less moist environment. That just means that your outgoing long wave radiation can be much cooler and much higher. And so an atmosphere that is more aggregated would be more efficient at cooling off to space. And so I think this was the sort of these findings were the findings that triggered a lot of research in this area, because there is also this idea that, or some models show that aggregation changes with temperature. So especially there was an initial study that found a very clear relationship between you increase the overall temperature and you have more aggregated convection, and that would have acted as like a negative feedback to climate change. So you basically increase the temperature elsewhere, or for other reasons, the clouds become more aggregated in the deep tropics. That allows more radiation to escape to space, and that wouldn't counterbalance the global warming, but there would be a negative feedback. And so people are really interested in whether or not this is going to happen. To kind of just spoil this, I think it's still unclear of how much this effect is relevant, but I'll also talk about this more in a second. The other thing that cloud organization does, it also impacts precipitation. So again, of course, you can see that it impacts the distribution of precipitation. But what actually happens in these simulations, the way they are set up, the total amount of precipitation you have has to stay the same. But because they sort of aggregate all the precipitation in one region, you can show that things like extreme daily precipitation are stronger if the clouds are more organized. So aggregation of clouds in sort of into these mesoscale clusters really changes all the aspects we are interested in, and that ranges like across a broad spectrum, from extreme precipitation to the radiation budget. They change entrainment, so you name it. The aggregation is really has a big impact. At the same time, as I said, also assessing how important these mechanisms are in the real atmosphere really remains an open challenge, because there's this huge gap, right, between what the atmosphere actually looks like and what we simulate in these simulations. But so just to leave you with this for now, there are other forms of organization that are sort of observed very regularly, that are very clearly occurring in the deep tropics, and that clearly impact things that we care about. So one example is our mesoscale convective systems. So clouds can be organized into these larger systems that have distinct vertical motion profiles compared to isolated deep convective cells. And there's sort of a classic study, or a classic review, I should probably say, from House from 2004, so already quite old, that looks at what's or that kind of summarizes this effect. So what basically happens is you have these organized clouds. They produce a large anvil or like a large region where you have stratiform rain. So you have your deep convective core, but then you have this stratiform region that also rains. And the convective core and the stratiform region produce very different kinds of heating rates. And you can see that sort of in the figure here, where you have the dashed line gives you sort of a heating rate, and you can in your head sort of translate that into vertical motion. And so you can see the convective part has this heating rate that peaks sort of in the mid-free troposphere. And then the stratiform part has this dipole heating structure and also this dipole vertical velocity profile. So actually sort of downdrafts below the anvils and updrafts and sort of higher up. And so then depending on how big your stratiform region is and how big your convective region is, the overall vertical velocity profile you get in this convection depends just on how organized your clouds are and what kind of sort of stratiform regions they produce. And so why is that so important? I mean, on the one hand, of course, it's important because stratiform regions will reflect sunlight differently and also trap long-wave radiation differently. But it's also interesting to think of this if you think of the vertical velocity profile, because as we said before, how top-heavy or bottom-heavy the circulation is kind of sets how efficiently energy is exported. And so you can see that like the key sort of properties of what sets the vertical motion profile really change with how organized the clouds are on a mesoscale. It's not only clouds sort of clumping together, so both in like aggregation and mesoscale convective systems, kind of about like clouds sort of forming a cluster of clouds. But you can also show that mesoscale organization can change the vertical velocity profiles if you have sort of different patterns of cloud formation. And what do I mean by that? So I'm going to talk about something that's kind of become known as edge intensification. And this is actually something that I've also worked a bit on. So I thought it might actually be fun to sort of take you on a trip on how this kind of particularly about how sort of I interacted with this topic, because it kind of emerged from a ship campaign that I was on. The ship campaign was on board of a German research vessel, and we crossed the tropical Atlantic in boreal summer of 21. And you can kind of see our ship track outlined here on the left-hand side by this dashed line. And so we crossed the Atlantic ITCZ in this north-south direction. And what was interesting for us during the campaign was to look at the satellite images, because what they showed was these two bands of clouds that actually marked sort of the outer edges of the ITCZ. And we were particularly lucky that we kind of actually, the band was where we were at one point. And so you can kind of see the yellow dot on this left plot, which marks the location where the ship was when the satellite image was taken. And so this is actually curious, because this idea of that the ITCZ has edges seems, on the one hand, it seems quite obvious when you think of it as this region of mean ascending motion and region of mean sort of high column water vapor. But if you think of it like on an instantaneous, as an instance in time, you might think of it as just a confluence line. So just the line where the trade winds meet. So the northerlies and the southerly trade winds meet, and that's where you have the ITCZ. And we found that this is actually exactly what happened at this northern cloud point. So if you look at the meridional wind speed that's shown in the graph here on the right-hand side, so if V is smaller than 0, then the wind's from the north, and if V is larger than 0, the wind is from the south. And you can see that at this dotted line, this is when we had the confluence. And when we were on the ship, we all thought that, yeah, that makes perfect sense. Now we've crossed the ITZ. Yeah, all good and well. But then somehow we were in the ITZ. And in the ITZ, I also mean, for example, given the high humidity content that we measured when we were on board. But then we passed this sort of second cloud line, and we encountered another convergence line, which was a speed convergence line. So instead of having two sort of flows in opposing directions, what we actually saw was that the southerly sort of actually slowed down at this location. And that, of course, means, again, that the air has to come up, or it has to go up, has to go somewhere, and it went up in this case. It didn't have so much choice, actually. But so the upgoing air was then what marked sort of this southern edge of the ITZ. And so now, of course, you can ask, well, okay, so you crossed the Atlantic once. It is in this very specific state that's a bit maybe peculiar, but how interesting is that? And so what we showed is you can actually generalize these results, and you can basically always identify sort of the confluence line and the speed convergence line, and then you can just look at how far are these apart. And what you find is that there's a median distance between these edges, which is around 500 kilometers. So that's like a substantial difference. And actually only in like 10% of the cases do these edges kind of closer than 200 kilometers. And so now, okay, now we've defined the edges of the ITZ. What we can now do with this is we can calculate composites with respect to these edges and to the width of the ITZ. Because so why do you usually not see these edges? Well, because as you know, the ITZ is dynamic on like a day-to-day basis, right? So you have the ITZ moving sort of north and south. It becomes wider and narrower. And if you average over any given, like a long enough time period or a large enough spatial region, then you sort of smear out the signal, and so you won't really see it. But if you now pick these two edges and say like, we're compositing with respect to these two edges, then you can actually try and see what happens inside and what happens outside and what are sort of their properties. And that's exactly what we did. So what you can see here on the right-hand side is the meridional velocity field again. So like the one we measured on the ship, but now from the reanalysis data. And the different colors are just differently wide ITCZs. And the different the different dotted lines are basically these two edges that we composited with respect to. And so if you look, for example, for the cases when the ITZ is pretty broad, you kind of reconstruct this this meridional wind speed profile that we saw before. So at the dotted line, the wind speed changes from northerly to southerly. Then you're in this region of like reduced meridional wind speed, and then you have a speed convergence line. And why do I think this is interesting? Well, I think this is interesting because suddenly a line turns into two lines, and that means there's something that happens between these two lines. And we called this the inner life of the Atlantic ITZ, and we then basically just repeated this compositing we did for the meridional wind speed. We repeated that for a number of different properties that we were interested in. So for example, we wanted to know where does it rain the most, and where is the OLR has the smallest value, and how does it relate to sea surface temperature and so on. And I'm not going to go through this schematic because that would take way too much time. But one thing that I wanted to point out is that, for example, in boreal summer, what we found is that peak precipitation actually doesn't happen at the location of confluence, but at the location of speed convergence. And I think Divya already gave a presentation last week. And so, yeah, we are thinking that her results and these results are really very much sort of connected. One thing that is important to note is that even though convergence seems to be intensified at the edges, doesn't mean that you never have any convergence inside this region anymore. And so you can still have convection. You can also still have the dominant amount of convection in between these edges. But if convection is just happening along these edges, then we refer to it as edge-intensified convection. And again, okay, you might wonder, okay, it looks kind of cool on a satellite image, but is it really so important? So would we really, is that something to kind of consider because it's important, like more generally? And I think there's some indication for this to be true. So there's a study by Hiro Masunaga where he also looked at edge-intensified convection, and this schematic is sort of adapted from what he's found, but it's actually is made by Marty. And what you can see is that on the left-hand side is sort of the example for you have convection that peaks not at the edges, but in the center of the ITZ. And what Hiro found in his study was that the vertical motion profile was very deep. You can also see that on the right-hand side in the schematic. And that meant that he found, if you looked at sort of how efficiently this exported energy, that was really efficient. It's a deep overturning circulation, single convergence line. So this is kind of the classic thing you think about. But then he found that this edge intensification actually was connected with like a shallower vertical motion and an energy import. And he found that the right-hand side was by no means rare. So I think on average, he even found more edge-intensified cases than not edge-intensified cases. And so you can see if you had like these two cases, they will obviously kind of combine to make up the mean vertical motion profile. If you want to understand the mean vertical motion profile, maybe you'll have to understand what causes these structures and what causes the frequency of these structures. And just as a side comment, because I talked about this on Monday, what we find is that if we have strong edge intensification, then like in this case that I showed you before, and you look at the wind speeds between, the surface wind speed between, then you often find extended regions of very low wind speeds, which are these doldrums regions that I talked about on Monday. And then again, so in these regions you have subsiding motion, so that will impact your sort of overall mean vertical motion profile in a non-trivial way. And so what I really wanted to show with this was that mesoscale organization of clouds impacts sort of key properties of the clouds and the environment. So if you aggregate convection, cloud properties change, and for example, large-scale humidity changes, and that has a strong impact on the radiation budget, for example. If you have mesoscale structures that are sort of like observed mesoscale structures, mesoscale convective systems or edge intensification, and both of them have been shown to kind of impact the vertical motion profile. So both of them should kind of impact the efficiency of energy export. And so one thing you might wonder is, why do I talk about this now, given that GATE happened 50 years ago? They already stated mesoscale processes are things that you have to account for. Why is this sort of a topic that is kind of coming up now again? And I think because over the last decades, we've learned that convective parameterization schemes are tricky, and it's a bit unclear of how well they work, in the sense of they can lead to very different results. And one way of kind of showing this is that you can look at really idealized simulations again. So this time these are aquaplanet simulations. And what you can see is that you have, or what happens in an aquaplanet is you kind of take away the land, you make the sun sort of, you put the sun over the equator. You do have rotations, in contrast to your self-aggregation simulations. These are already more complicated, but still, of course, they're highly idealized. And so you set up a couple of different climate models in this way. And then you see what happens if you apply uniform warming. So you apply uniform warming, and then you can ask, for example, how do the tropical rain belts change? Because this is, of course, something you're really interested in. And this is what's shown here in this figure. So how does the precipitation change if you apply a uniform warming to the set of aquaplanet simulations? And so what you can see immediately is that the changes in precipitation are hugely different. So if you compare, for example, the left model with the right model, the one actually shrinks, the other one widens. And what that just means is that even in sort of their simplest setup, these models do not agree. And what has been argued is that one of the key differences between these models, there are also other differences, but one of the key differences between these models is the way they parameterize convection. And so this is kind of driven this idea that we have to get rid of convective parameterization schemes, and the way we get rid of convective parameterization schemes is we increase the resolution. So this is what's kind of happening at the moment, or it has been happening for a while, is that there is a push towards global storm resolving models, where you have horizontal resolutions of like on the order of a kilometer that can now sort of resolve deep convection explicitly. And so you do not need to have a convective parameterization scheme anymore. And you can see what this looks like here in these snapshots. So these are from the Diamond project. There was a comparison project of global storm resolving models. And so all of these models were run globally, but I just thought I would show you these sort of snapshots, or these like zoomed in selections which focus on the tropical cloud fields close to a tropical cyclone. And you can just see how much structure you can represent in these models. And you can also see how different they already look. To some degree, they look very similar. To some degree, they look different. But if you think of what I've talked about until now, you can maybe already guess that these different kinds of organization will feed back on a larger scale. And so that's exactly where we are at the moment. We are asking this question of whether can these models now represent mesoscale organization correctly? And if so, is that sort of a missing puzzle piece that has kind of hindered us in the traditional climate models of representing, for example, the tropical rain belts correctly? And yeah, so there's sort of in parallel to this development in the modeling, there's also now, of course, development in observational studies. And so I want to just kind of quickly teaser this here. So we had a campaign in 2024, the orchestra campaign, which returned actually to this area where GATE happened exactly 50 years later. And compared to GATE, we were really small. So we had 3 aircraft and one research vessel and 2 observatories. And so the overall objective of the orchestra campaign were like really much in line of what I've sort of presented so far, is sort of ask the question of what drives mesoscale organization in the tropics, and how that impacts both the smaller scales and the larger scales, and how that's sort of connected to the structure and the variability of the Atlantic ITZ. And of course, these observational campaigns are also motivated by the fact that we're having increasingly amazing observational data sets from satellites. So the campaign was very much aligned to also validate a new EarthCare satellite, which can actually give you vertical motion profiles, for example, within clouds. But as I said, also sort of to benchmark these high resolution storm resolving models that are sort of arising. Yeah, and with this, I actually want to summarize. So what I just wanted to basically point out is that on short time scales, the ITZ is not an extended region of large scale ascending motion, but instantaneous ascent is limited to within a very small fraction of the tropics and only occurs within the clouds. And so most of the tropical air at any given time is actually subsiding. And the mean overturning circulation sort of emerges from the combined effect of these clouds. So if you want to understand the ITZ, that's fundamentally a task of scale interactions. So clouds shape the large-scale circulation, and the large-scale circulation shapes the clouds. And so for mesoscale cloud organization, we think that they will modify these interactions. But I also want to point out this is a really active field of research, and that's been sort of fueled by these high-resolution storm-resolving simulations, where we can explicitly look at these effects. And so why we think that it might be important is that we see that if cloud organization changes on the mesoscale, that impacts the vertical motion profile. For example, as has been long known in mesoscale convective systems, but which is also now kind of apparent that also is also true for different patterns of cloud organization. And that, of course, impacts sort of the mean vertical motion profile, which could then feed back on the efficiency of energy export. And another a classic example is sort of self-aggregation, where that has a huge impact on environmental humidity, which would then also feed back on the radiation budget. But again, how relevant this is for longer timescales is unclear. And so, yeah, this is just what I wanted to basically say. The large-scale tropical circulation emerges from organized cloud systems across many scales. And if you sort of want to have a picture to keep in mind, these are just different stripes of the East Atlantic, ITZ, just basically 15 days in a row. And you can easily trace out where the ITZ is in this picture, but you can also appreciate how much the ITZ changes just from one day to the next. Yeah, and I think I should probably stop, and I'm happy to take any questions.
Thanks, Julia. We have time for questions. Julia, can you say a little bit more on benchmarking that you mentioned in one of the bullet points? Is there good enough data sets, observational, that can directly inform diagnostics for next GEMS? Or?
Yeah, so I mean, one thing, for example, that has been done at the Max Planck Institute is that people have looked at the EarthCare satellite measurements and then directly compared them to limited area model simulations. So you get a really direct comparison between the two. And then you can just see how much can you actually use, for example, a limited area model in this case, to study the processes that you're interested in. And I think it's been argued that because the data is starting to look very similar, so you can actually, the limited area model cross-section looks very similar to the satellite cross-section. You can actually do this interaction in a quite meaningful way.
Hey, Julia, this is Spencer Hill. Thank you. That was great. I don't know if you're able to share your slides again, but the first snapshot you showed of the wind profile with latitude, and you pointed out the confluence and the speed convergence.
Yeah. Oh gosh. I'm always jealous of people who know how to navigate this more efficiently.
Same.
You mean this one?
Yes, yes. So
yeah,
in this snapshot, you point out that the other edge is the speed convergence edge.
Yeah.
And then you do these composites, but then by my eye, the largest convergence is sort of in the interior, right? It's that part sort of centered on 8 degrees latitude.
Yeah.
But then in your composites, it looks like the confluence area is both of the zero crossing and where you have a sharp gradient, like a strong convergence. And so I'm just trying to tease out, I've never thought about confluence until this week. But like, is there something special about the zero crossing in and of itself? Like, how do I think about that relative to just the straight magnitude of the convergence?
Yes, I think the zero crossing is still very, very meaningful in the sense that you really that's really where the trade winds are. It's a bit tricky in this picture, because what actually happened is that we were stationary at this confluence line, and then there was a cold pool that sort of caught up with us. So the reason this looks a bit more complicated than you would like it to be is that just for sort of measurement details. But I think the actual confluence line is still really the line that you care about, if that makes sense.
Yeah, I guess it's just an interesting coincidence then that also the just dV/dy is large there in these composites.
I wouldn't have thought it's a coincidence, because what happens so at least what happens in sort of idealized simulations is that you really get subsiding motion within, or depending, especially when you have a situation that looks like this, you get so subsiding motion within, and then then that sort of goes outward, and then you have something, then you have the trade winds going inward, and so the peak confluence of these points is where you have the peak convergence, sort of by. Yeah, that wasn't surprising to me. Maybe I should think hard about why this is surprising.
Hi, Julia. Thanks for the great talk. I have a question regarding the sort of the magnitude of the vertical velocities that you talked about. So let's say like you have an aircraft doing like a mesoscale circle, right? And you mentioned that the updrafts in the clouds are about like order of meters per second, whereas when you average it out, it's centimeters per second. So can you tell us, does the size of the circle matter, like in the magnitude of the vertical velocity that you get out of the measurement?
Yeah, that's exactly right. So what is important to note if you do these circles or these measurements from the ships is that you get like a horizontally averaged vertical motion profile. And so I think we are still in the process of, so this has been used really efficiently in sort of the in the subsiding branch of the head laser, where you can assume that the vertical velocity is much more homogeneous, and we're still having a project to now look at how robust this is. Now we have these circles that were sort of flown around deep convective updrafts. But yeah, so it's important to remember that they give a horizontally averaged vertical velocity. So we, if you look at the data that we have there, most circles have very small vertical velocities. If you manage to put your circle exactly around a mesoscale convective system, which happened basically once, that, yeah, that's the thing that you in the end see actually in the averaging.
Or to seeing the paper results from this.
Yeah, it's to some degree, of course, it's exactly what you expect, but on the other hand, it's also then you have 90 vertical motion measurements, and in the end, it's basically two that actually matter. I mean, I'm exaggerating a bit, but it's kind of two that set the mean.
Hello. Hi, Julia. Chetan here. Really nice talk. Thank you. Thank you for the talk. I would like to know your thoughts about the Arakawa-Schubert scheme that you showed earlier. So at subgrid scale, the type of cloud, the number of cloud, and its distribution is what matters, but really hard to measure in the real world. Now that there are cloud resolving models, storm resolving models, what are your thoughts about using these models to modify or update the Arakawa-Schubert scheme?
Yeah, great to hear from you, Chetwa. I'm sorry I didn't get the chance to meet you in person again, but yeah, so interesting question. I think this is going to be interesting because to some degree that's the kind of counter test you want to do for testing whether the mesoscale organization sort of matters, because I think if you're able to because what in the end Arakawa and Schubert, of course, does is it sort of says, I only kind of care about the cloud population, and I don't really make any assumptions of, for example, how they're organized. Then, and if that works, then that's sort of small scale to large scale. And I think it's actually would be a good way to sort of have that as a comparison for, because I think to some degree how well that works will also tell you how much of these mesoscale organization processes we need to account for.
Thank you.
If that made sense.
Hi, thank you for your talk. I was wondering that since you mentioned the gate circle data, the hexagon data, is it still publicly available, and can we use it, and is the measurements like usable?
Yeah, I think it's still available, or at least I know that Gilles has it. I think the problem is a little bit that we now think they had maybe few ships, but they still but yeah, it's still available. It's still processed data. So I think, yeah, we probably like with most of the data from the GATE campaign, we should probably try and use it more. So yeah, I would definitely encourage looking into it. And we are currently actually preparing some of the original GATE data, which doesn't actually include the hexagon measurements, but sort of the other measurements to see, just to make them also more publicly available, because especially with the orchestra campaign data, of course, it's a really interesting set of data to just kind of return to the same region 50 years later.
Thank you.
Thank you for your talk. My question is about the cloud cluster. So clusters means when there is a confined region where updraft is going on. My question is about the subsetting branch, where this subsetting is going on. It is also confined within that region, or it has some kind of distribution?
So you mean in these cases, for example? Yeah. So you actually develop something that looks a little bit like a point symmetric Hadley cell. So what happens is that then if you again look at mean vertical motion profiles, then what it would look like is basically you have sort of ascending motion within this cluster. So you can think of it like within this white line, and then you have subsiding motion around it, and you actually get a circulation that develops. And so you still have instantaneously, it's the same as sort of always, you still have instantaneously, even within this cluster, you have subsiding motion, but if you average over a longer time, you develop, you again sort of recreate a point symmetric circulation around this cluster.
Oh, okay, thank you.
Or like a radially, yeah, you can think of it as like an odd version of the head lasers. Rather than having a band of convection, you have sort of a circle where you have rising motion and then subsiding region that develops around it.
Okay, thank you.
But if not, let's thank Julia for a very nice talk.